All right, we should be live. Hey everyone, let's see. Someone's got to acknowledge my existence, and then we can know that we're actually live. Let's see, and then we'll get cracking. There we go. I see someone saying it's live, so that's good enough for me. So hey everyone, Fraser here again for our Monday open space where we just answer your questions about space and astronomy, talk about what's going on. And today I've got a special guest, which is Dr. Brad Peterson, who is, what is your official designation with the LUVOIR project?
I'm the community co-chair. The other community co-chair is Deborah Fisher of Yale.
Great, okay. And Brad has come on the Weekly Space Hangout a couple of times, and I've reported on LUVOIR now several times in the Guide to Space and in other places. We've talked about the upcoming super telescopes, and we just did an episode about a month and a half ago just about the four big telescopes that are in the works: HabEx, Lynx, the Origin Space Telescope, and LUVOIR. And LUVOIR is the one that I think everybody is most excited about, just because it's just like pushing the very concept of science fiction. And but I figured, and everyone was really excited, had tons of questions, and so I thought I would have you come and join me, and we'll talk about it. So let's go back then, and for anyone who has no idea what LUVOIR is, can you just give people a bit of a background on it?
Sure, yeah. The background for these four missions goes back to about 2013 when the NASA Astrophysics Division realized that they weren't really going to have anything quite ready for consideration by the next decadal in 2020 unless they got some studies going now. So the first thing they did was an Astrophysics Roadmap, which is a 30-year vision for what NASA Astrophysics ought to be doing. And each of these missions, well, let's see, three of the four missions actually came right out of that Astrophysics Roadmap. They're the things that NASA desired to do on the time scale of 10 to 20 years from now.
And just to clarify this in people's brains, right? The decadal survey, this is the wish list that that astronomers put together and then deliver to NASA and say, okay, based on what we know today, these are the big questions that we have next, and will you please, when you're building telescopes, consider these priorities, right?
Yes, that's right. The study is actually undertaken by the National Research Council, and they do this again every 10 years, and we prioritize the science, and in some cases you prioritize actual facilities that we want. The James Webb Space Telescope was actually recommended by this process, as was WFIRST.
Right. I mean, most telescopes that people are familiar with have all gone through this process. I mean, not just James Webb WFIRST, but even a lot of the smaller instruments, Earth-based instruments,
yes.
Various instruments in other wavelengths. It all goes through the same process. The astronomers make their wish list. They deliver it to NASA Santa Claus. And then at some point over time, the presents get delivered. And so where are we in that cycle right now?
We are going to begin the decadal within the next several months. In about December, they will announce who the chair is, and then they will start populating the committees. And they should be done with their work in about 2021.
And so this is really crunch time. I mean, it's going to come together pretty quickly, and then by 2021, you're going to have this final set of recommendations. But I guess your work and the work from the other project managers is to come up with what kind of instrument will probably fulfill the requirements of the astronomers.
Yeah, our actual committee is called the Science and Technology Definition Team. So what we're supposed to do is identify the science that needs to be done in the next generation and define the technologies that we'll need to do that so that NASA can then fund those technologies and we can build a telescope.
So let's talk about LUVOIR specifically then. Where did the concept for this telescope first come from?
People have been talking about a bigger version of Hubble since the mid-1990s. There have been previous studies, in fact, that were done to define how big the telescope had to be and what the instrument suite had to be. And we've been able to build on a lot of that previous work. So we started our work then in early 2016. And again, because we had these earlier studies to look at, we were able to come up with what we thought was really interesting science right away and come up with the technologies that we need. So just to give you an example, a couple of the technology tall poles that we have to figure out how to take down are, for example, high contrast coronagraphy to look at exoplanets around nearby stars. To do that, we have to suppress the light from the star by about a factor of 10 billion.
Yeah.
Yeah, so, and going with that, then we also have to have an extremely stable platform. The telescope has to point in the same direction all the time at a very high level of accuracy for us to hope to do that. So those are, for example, those are two things that we've identified and that people are working on.
This whole idea then of the coronagraph, I mean, we've talked a bit about the coronagraph as it relates to James Webb and other telescopes as well, and this is this idea of blocking that light from the star. And I know there's a couple of ideas in the works. One is an onboard coronagraph that's going to be on the spacecraft, and another is something that's floating far away. It's some kind of sunshade idea that would then provide. Would both be part of the package for LUVOIR?
For LUVOIR, we're going with an onboard coronagraph simply because a star shade will have to be a separate mission because it would have to do precision formation flying about 100,000 kilometers away from LUVOIR itself. Yeah. So yeah, that's a separate mission, and we're looking at that as that's an eventual add-on.
And just as a sense of scale then, right? Hubble Space Telescope launched in the 80s.
In 1990.
1990, but then had to be fixed,
right.
But has been producing images now for close to 30 years, which is kind of amazing. I think they celebrated 20. And it is so if I get this right, it's a 2.6 meter mirror.
2.4 meters. 2.4 meters.
2.4 meters, yeah. I got every single thing wrong. 2.4 meters. So how big are you hoping that LUVOIR is going to be?
We're designing two architectures. Basically, for the reason of trying to understand the scalability between them. So our dream LUVOIR, which we call LUVOIR A, we just packaged the largest segmented mirror that we could in the largest rocket fairing that we could find that is in the planning stages, which is the Space Launch System, the SLS Block 2. That has an 8.4 meter fairing, and we can fit a 15 meter segmented telescope in that. So that's our preferred architecture. We also had to ask ourselves, well, what happens if SLS Block 2 isn't there? Because, for example, I mean, that's really being made to go to Mars. And if we're not going to Mars, are they going to make it? Then what happens? Well, we looked at other fairings as well, like the SLS Block 1, or some more conventional ones, Falcon Heavy, for example. And with those, the largest telescope that we could package would be about 8 to 9 meters, depending on how exactly we do it.
Right, so this idea of a 15 meter telescope, again, back to what we talked about, if Hubble is 2.4, 15 meters is bigger, much more bigger. So if you could get that full scale, how much more sensitive would LUVOIR be compared to Hubble?
Well, depending on it'll be a lot more sensitive than Hubble, depending on precisely the application. If you're doing, things that are point sources and your background limited, then the performance scales like the diameter to the 4th power. So it gets to be a pretty big advantage to go to a really large telescope.
Right, and just to give people, again, a sense of scale, right? When you look at the Hubble, like, it can see directly galaxies that are several billion light years away, and then you get these unique situations where Hubble gets a gravitational lens and can actually use a foreground galaxy as a way to see even farther beyond to just, in some cases, hundreds of millions of years after the Big Bang. What will LUVOIR be able to do just brute force?
Well, there's, just sort of brute force. Things that I always think about are the fact that with LUVOIR, you can get an HR diagram down to the main sequence turnoff point for any galaxy out to about as far as the Virgo cluster, which is 20 megaparsecs away. You can get a Cepheid distance for any galaxy out as far as the Coma cluster, which is 100 megaparsecs away. And then beyond that, you don't need it, because by then you're into the Hubble flow and you get distances from redshift. So there are all these things that you can do. You can observe the proper motion of individual stars in the nearest galaxies in their nuclei, which will tell you what their dark matter profiles are. And that's something, you know, I don't know how to do that any other way, but we can do astrometry, you know, at the sub-milliarc second level.
And it's not just that as well. I know when I was working on my last video about LUVOIR, it will be able to be doing stuff within the solar system, like high-resolution images of Enceladus, Europa, anything really you want to look at. And I guess that's the key, is that it is this Swiss Army knife, like the Hubble Space Telescope.
Exactly. So, you know, in a sense, more than any other mission, this is the real successor to Hubble, because it has the same sort of wavelength capabilities, and it's going to work over the same part of the electromagnetic spectrum, and do some of the same science, but much better and much deeper. In some cases, 100 to 1,000 times as sensitive as Hubble.
There you go. That's what I wanted to hear. 100,000 times as sensitive as Hubble.
100 to 1,000.
100 to 1,000, right?
Yeah,
not 100,000. 100 to 1,000 times as sensitive.
Don't overpromise.
Yeah. No, that's good. Well, that'll be for the next generation telescope. All right. So let's talk briefly about those different. Now, you mentioned the 15 meter is the A class version, and that's if the SLS is flying.
Yes.
That's. I mean, is that if the SLS is still flying, or like, can you sort of explain that part of it?
Okay, well, that has to do with whether or not they build the cargo Block 2 version, which is the one that they were going to use to send equipment, to pre-position equipment for missions to Mars. But that's a very big rocket. It's going to be very expensive, and it's not clear that it will be built if we aren't going to Mars soon. If we are going back to the moon soon, they will be building an SLS Block 1, which is somewhat smaller.
Right.
So yeah, LUVOIR B will either fit in that, or we've also looked at the option of using something like a Falcon Heavy.
Would the A fit in the Falcon Heavy?
No, it would not.
Okay.
It's too big.
Okay, so we would need to go smaller. Now, it would probably fit in a BFR should such a creature actually eventually arrive.
Yeah, we're actually still trying to get all the specs on that to see if it will meet our needs. But yeah, basically what we have to do is figure out how to get 45 metric tons to Sun-Earth L2.
Now, just to talk about that orbit, I know James Webb is also going to that Sun-Earth L2 point, and it's only going to have about 10 years of fuel to be able to hover in that place. We've had Hubble for close to 30 years. I'm guessing people could keep using it for another 30 years if it could keep it going.
Right.
Will you have that same kind of time limit like what James Webb is going to have?
Well, the way flagship missions are designed, they're designed for a 5-year lifetime, and that means that they'll easily go for 10. My own personal version of LUVOIR, or vision for LUVOIR, is it should be a facility. It should be like ground-based telescopes, built to last, or intended to last, 50 to 100 years. So we are making LUVOIR completely serviceable. The only part that we really can't service is the optical telescope assembly itself. But all the instrumentation and the spacecraft bus and the sun shield, all of this stuff should be in principle replaceable. So then we have to figure out, how do you do that?
Yes. Yeah. Well, at L2 Lagrange point, but that is the kind of mission that you would hope that a future astronaut corps with Orion spacecraft and some of these other things should be able to get out there and visit. I mean, hopefully. Yeah.
Well, yeah, in fact, that was one of the things that really concerned me the most, is to really get, to amortize the cost of LUVOIR, which is going to be high. It needs a long lifetime. So that means it needs to be serviced. So how do you make that happen? So I actually when I was chairing the science committee for the NASA Advisory Council, I spoke to my counterpart in the Human Exploration and Operations uh, program, Ken Bowersox, a former astronaut. And I kind of pulled him aside at a meeting and said, well, hey, Sox, how would you feel about going to Sun-Earth L2 to service a telescope? And of course, you can imagine an astronaut's reaction is like, you know, I'm there, baby, you know, so.
Yeah.
But subsequently, we've thought about other ways that we could do this. And one very intriguing possibility is to make use of, well, I can't remember what they're calling it now, but this deep space
The
gateway.
Deep Space Gateway, yeah.
Yeah. A small space station that will be in lunar orbit. And it turns out it takes a very, very small amount of energy to go from a cislunar orbit to Sun-Earth L2. And you could, it's so small, it's like tens of meters per second, and delta V that's required. And you could do this with an ion engine so that the accelerations could be very gentle, and the telescope you don't have to worry about it shaking apart under acceleration, and you wouldn't have to worry about a fuel plume contaminating the optics. So there are ways to do this that aren't science fiction and aren't crazy.
Well, let's talk about science fiction and get a little crazy, which is, it's a strange time. And when we talked, we had talked last time, and I think maybe a year ago plus, and things were a lot less certain at that point. And so there was we were sort of more spitballing ideas, and everything from something that is going to be rolled up inside an SLS and kicked off into L2 to something that maybe could be constructed in a different orbit and maybe astronaut service and maybe more connected to it. And we're at this point now where space-based construction is starting to be seriously considered with what the Made in Space people are doing with their Archinaut.
International Space Station. I mean, that was assembled on orbit.
Right.
So yeah, we can do this.
Yeah, and so back to that. I mean, is it difficult at this time when all of these new launch programs are coming on board, that all of these new methodologies are coming on board, new capabilities, to then try to plan out a mission that may feel like it's not taking best advantage of all of the new pathways that are coming so quickly?
Yes, and it's always been this way. It's always been difficult. I mean, just if you keep in mind how we did the Apollo missions, the lunar orbit rendezvous turned out to be the best strategy to get astronauts back from the surface of the moon. And that was an idea that just suffered scorn for a long time until people realized it was the only way that you could do it in the foreseeable future, because it's only getting a very small amount of mass off the surface of the moon and into lunar orbit that was required. So yes, a lot of times these ideas take a long time because they don't always strike you at first as the most conservative or lowest risk engineering. But sometimes when you study them a little bit better, you find, yeah, this is the way to do it.
Now you've talked about the budget briefly. What are you sort of estimating right now that things are going to cost?
Well,
or what budget have you got to work with?
Well, we don't have any budget to work with right now. Right. It's all notion. So we've been very reluctant to say anything about what we think these things are going to cost, because the minute someone says something that is going to cost something, that becomes the number.
Right.
And whether it's too high or too low. So what we're waiting for is when we send our final report into NASA. NASA then will send it to the Aerospace Corporation, who will do an independent cost assessment. They will assess both cost and risk, and they will come back with a number, and that will be the number. So before that, it's just kind of it's speculation. People guessing from various scaling laws that are sometimes grossly oversimplified. So we're trying to do a good job of this.
Yeah. So let's get on. I know some people had some questions for you. So let's talk a bit. Let me see here. And remember, if you can put a question mark before your question, that would be great. So Eric Sorensen asks, is it possible to design LUVOIR to have a modular main mirror so that it could be expanded late in construction depending on the launch vehicle? So not launching it in one fell swoop, but maybe figuring out a way to construct it like the space station in orbit bit by bit.
Yeah, we have talked about that some, and there are um, some advantages and some real disadvantages. The problem is that uh, the biggest problem is that as you make it big, if you start out at the center and then make it bigger, the focal ratio changes. So every time you add a ring of mirrors, you need all new instruments. So
right.
yeah, so that's a bit of it. The focal length changes. So yeah, that gets to be something of a problem.
With because if it's a parabolic mirror, like if it's a spherical mirror, is it different creature? But or is it just
you wouldn't want a spherical mirror. So
right? So you would always want, so each time you added another ring of mirrors to it, every time you change, you would have to change the instruments that you're using on board, which, I mean, is sometimes a good opportunity to change those instruments anyway. I mean, the instruments on Hubble have been upgraded and modified over time as well.
Absolutely, but you have to remember that the cost of the instruments is something like a quarter of the cost of the mission. So the instruments are a big deal. It's a big investment.
Yeah. So, okay. Now, a couple of people are just mentioning ideas about putting a telescope on the moon as opposed to putting it out in deep space. Have you looked at the ideas of putting something on the moon? And there are some advantages to that?
Yeah, actually, for an optical telescope, UV telescope, the moon is a terrible place to put a telescope. You can only use it half the time because it's going to be in the sunlight. The moon is a very dusty environment, and judging from what the Apollo astronauts found, it's sticky, clingy dust, and there's just no point of bringing something massive deep down into that gravity well when you don't need to. Space is a much better place to observe, and Sun-Earth L2 is very good because you're able to maintain a fixed temperature because you're always at the same illumination from the sun. You're always in communication with the Earth. It's always looking in the anti-sun direction. So that's a much better place to do astronomy than
We've mentioned that several times on the Guide to Space. The gravity wells are for suckers. Like once you've gotten out of a gravity well, why on Earth, why in space would you ever put yourself back into a new gravity well? But having a place that you can actually walk around and tinker with and upgrade. I mean, there are some advantages to being down on the surface of the moon, and the moon's gravity well isn't that bad, but there are definitely downsides.
There's at least, one application that begs for the far side of the moon is radio astronomy, where you've blocked out all of the radio noise from the Earth.
Yes, and block all the light, and that's one of the advantages to being on the far side of the moon. Is there's just no radio transmissions from Earth are going to make it out there. So Raj Luther asks, when LUVOIR has done its primary mission, can it be repurposed, for example, added to a space station or spaceship? This is a topic that actually just keeps coming up about Hubble, about the International Space Station, about the future of these tools and instruments after perhaps they've lived out their main lifetime. Everyone sort of feels that it's such a tragedy to burn them up in the atmosphere or let them, to imagine James Webb drifting out of the L2 point just out into space is heartbreaking.
Yeah, well, this is part of the reason that I've gotten very interested in how you service telescopes at L2, because I think people are going to have a real hard time dealing with it when James Webb is lost all of its propellant and can't maintain station anymore. And it will simply be abandoned. And that's a pity for the investment that we put into it, not only in dollars, but in years.
Yeah.
So this is, again, why we're thinking about LUVOIR as something that we can use for a long time, just as we do with ground-based telescopes. Ground-based telescopes, in many ways, they have nearly indefinite lifetimes. It's very rare that a telescope actually gets completely mothballed.
Yeah. And there are, they're not going to lose sight of where James Webb is. It's just going to be not doing its main job anymore. But I can sort of imagine, right, that there are all these these advanced ideas. Let's make it human serviceable, or let's give it an ion engine, or let's try using a solar sail. And at a certain point, it's too much technical uncertainty, too many, and this comes back to the challenges that they had with James Webb. I mean, part of the problem with James Webb is they just had too many, or so many, technical uncertainties, brand new technologies that were developed, and you're seeing the collision of all of those technologies revealed in the slipping timelines and over budget.
Yeah, let me say a couple things about that. One is, it would be hard to service Webb in any case because it's going to be operating at a temperature of 40 Kelvin.
Right.
So, you can get to the near side, so you could probably service the bus. You might even be able to refuel it, and there is some talk of that as a contingency, but there's not much else you can do. But actually, the most recent delays on Webb haven't really been because of technology development. They've been process failures. They're things that were just done incorrectly. Now, earlier on, the reason that there were huge delays is that from the very beginning it was under budgeted, and that just went back to the fact that a previous NASA administrator in the 90s said, we're not going to do any more billion-dollar missions. So these missions that were already well along in their planning just did their level best to not look like they were going to be billion-dollar missions, and hence your overruns.
Right. Now, one of the things when I talk to astronomers is they obviously love what the Hubble Space Telescope is doing for them, and what about, and when you look at James Webb, for example, it maybe is multiple Hubble Space Telescopes of cost, and right now Hubble is dramatically oversubscribed at this point.
Yes.
Can you explain that thought process between putting more smaller but capable spacecraft up that would give more bandwidth for astronomers, as opposed to putting something a lot larger up there, right?
Well, yeah, to start out with with the very large things, we put the very large things up there to do the things that we absolutely have to have very large things for. But NASA maintains a rather broad portfolio of space telescopes of various size, various complexity, and various cost. The Explorer program, for example, are telescopes that I'm not sure what the cost limit is now. It's between 200 and 300 million for the whole mission.
Right.
And, yeah, and they do great science, but they do the great science they can do with that particular size telescope. Hubble, there are still lots of good things that you can do with it, but if you really want to push the envelope, if you want to do some of these things that are impossible for Hubble, you have to have something like a LUVOIR.
Yeah, yeah.
So that's the whole point of LUVOIR, really, is do what we now consider to be impossible. Just as with Hubble, we were doing things with Hubble that were impossible to do from the ground.
Right. And I don't know. I would be interested to, I guess, but the point is like, to make more Hubbles, to have more time on the Hubble Space Telescope is one thing that is impossible for Hubble right now.
Yeah, that's true. Yes, because a somewhat near analog to Hubble is WFIRST, and WFIRST comes in at 3.5 billion. Hubble wasn't cheap either.
Yeah.
So yeah, it's really a matter of trying to maintain what NASA refers to as a balanced portfolio, where you have very expensive high-end telescopes, and you also have ones that are less expensive and more special purpose.
So I guess the other interesting challenge that's starting to happen, I'm actually just working on a video about this now, about this idea of what the ground-based telescopes are doing, and at this point, what the very large telescope array out of from the European Southern Observatory with their adaptive optics system is getting really good at removing the atmosphere, pretending like the atmosphere doesn't exist, and starting to match the capability of a space-based telescope. Does that take some of the pressure off of things like Hubble? Because now you do need to really beat what a ground-based telescope can do.
Yeah, the guiding principle for space astronomy is you go to space only if you have to. So because it's a comparable telescope in space is going to be 100 to 1,000 times as expensive as the
Right.
same telescope on the ground. Now, they are getting very good at certain things like with adaptive optics, but there are certain limitations. You will never be able to get what we call the point spread function with an adaptive optics system on the ground as you will in a vacuum in space. So some things where you're doing, looking at things that are very high contrast, like exoplanets, for example, you're going to have to do from space for the foreseeable future. The other thing is if you want to do adaptive optics over a fairly wide field, we call multi-conjugate adaptive optics, you're limited by the size of the isoplanetic patch in the atmosphere, which means your field it can only be basically about as big as the individual cells of air that are passing around in front of the telescope. So yeah, and of course, the big one for me is ultraviolet doesn't penetrate the atmosphere.
Right.
And if you're doing ultraviolet astronomy, you've got to be in space.
Yeah, your X-rays, your gamma rays, ultraviolet, right. They all require being out in space, no matter how much adaptive optics you can do.
That's right. And same with most infrared astronomy. You can do some from the ground where there are windows of visibility where you're not looking at a lot of absorption from water vapor in the atmosphere. But if you really want to get a complete infrared spectrum, you need to go to space.
Right. So Arjun is asking, are space telescopes a narrower field of view than ground-based? So, I mean, are you going to have a smaller field of view? Is that part of the advantage?
Well, okay, we got an interesting trade-off here, right? Is that you get so much, the resolution that you get, the spatial resolution is so much higher in space that to cover a wide field of view, you need many, many, many pixels. So your instrument gets to be absolutely huge if you're making use of the actual sampling that you can get in space. So sometimes you're limited by the size of your detector. Now, let's take the case of WFIRST, for example. WFIRST is it's in terms of aperture, it's the size of Hubble, but it's much shorter, has a shorter focal length, and therefore it has a much wider field. So you'll be able to observe the images that you will get from WFIRST are going to be 100 times as big as the images that you get from Hubble. Same size telescope, just a matter of the focal ratio.
Right. So let's talk a bit about some of the fundamental science questions that you think, because I'm assuming this is where the whole thing is coming from. You mentioned some of the kinds of things like building an HR diagram of a galaxy. What are some of the fundamental questions that hopefully LUVOIR will be able to be used to help answer?
Well, I think what we think is the really compelling question. In fact, we think it's the most compelling scientific question ever asked is, are we alone? And LUVOIR will be able to provide a meaningful answer to that. We'll be able to observe and characterize the atmospheres of exoplanets with sufficient fidelity that we will be able to determine whether or not life is existent on these planets. We'll be able to observe enough of them that if we don't find any, we will know that we are alone at the 95% confidence level.
Wow. So let's talk a bit about how you will actually be able to do that. What technique are you going to be doing with LUVOIR to actually be able to observe these other worlds?
You're doing low-resolution spectroscopy of the exoplanets using the coronagraph. So the coronagraph blocks out the light from the star, and the light that we see is the light from the planet's atmosphere. And we look for particular constituents in that atmosphere, and we look for things that are, say, mutually unstable. If you find, methane and oxygen in the same atmosphere, that's a pretty strong indicator of life.
Maybe. I mean, I've heard that right now this idea of biosignatures, like what is the smoking gun for a potential life form on another world, maybe, there are natural processes that can generate some of these things like oxygen, like ozone, like carbon dioxide at certain levels, that actually figuring out that exact biosignature is going to be tough. But I guess over time spent with LUVOIR, maybe you will be able to do it.
Yeah, well, and people are thinking about this very long and hard now. I'm not an expert in planetary atmosphere, so all I can tell you sort of this top level stuff that,
Yeah.
that what you look for are things that would not naturally occur under at the same time. And the common example is methane and oxygen. If you see oxygen in an atmosphere, there are ways you can get that as a false positive, but generally it has to be generated biologically.
Right.
We know now.
Yeah, it's an interesting, and I hope by the time James Webb gets rolling, by the time LUVOIR gets rolling, that they will have settled on various methods to tease out that signal, and we'll have a standard practice to be able to do it. Now you say you said 90%. So in other words, LUVOIR will be able to directly observe a large enough sphere around us to give a definitive answer about this.
Exactly. Yes.
Wow.
So, yeah, I know it's pretty fantastic, and that estimate is based on the assumption that 1 planet in 10 will have an Earth-like planet in the habitable zone. And the last time I heard anything about the census, that number is thought to be maybe a little bit low. So the chances would get better and better that we could detect life elsewhere.
Right. This is always an argument that I give to people when they say, like, we shouldn't be sending a transmission out into space, that we shouldn't be sending the Voyager spacecraft out into space, when the reality is that Earth itself has been transmitting our existence for about 500 million years.
Yeah, that's right.
The jig is up.
Yes, that's right.
Right.
If they can observe us, if they have a LUVOIR, they know.
They know that we're here. Yeah.
Yes.
And then, of course, then it makes you wonder, where are they? One other idea, as I'm just trying to contribute some more ideas to the project, has anyone looked at or considered bringing back an idea of like the terrestrial planet finder back in the day, about running some kind of interferometer, run a bunch of separate spacecraft, flying in formation, combining their light together? Has that been considered again?
Yeah, it has been. But what we have done is we have settled back on a single aperture because we need collecting area, and we need to meet the meet the diffraction limit. And it just turns out that the most efficient way to do that is with a single mirror right now. Now, eventually, you'll want to go to an interferometer, but we're not there yet. That's a technology that's probably a little bit too far at this point.
That's when you get the next 6 LUVOIRs all launched in formation, and they're all flying in formation and then acting like an interferometer.
If you can figure out how to phase their signals, you're golden. So,
but space, I wish someone would launch one, because space is the perfect. We're going to see LISA, which is going to be this great example of trying to run an interferometer in space to find gravitational waves, and it would be great to see that attempted, because it's so powerful here on Earth for like the Very Large Array and other telescopes like that.
Yeah.
There was a question here that I wanted to get at. Right. Raj Luthra asks, will LUVOIR be able to look at black holes? Is it going to be able to help with that kind of astronomy?
Sure. Yeah. You'll be able to look at the center regions of galaxies, and the most important thing we can do is measure the masses of these black holes. But we can. This is what I do for a living, actually. So I measure the masses of black holes in active galaxies, and we have some ways of doing it. And what we would like to do is apply multiple methods so that we find out where the gotchas are.
Well, what's the best method for weighing the mass of a supermassive black hole right now?
If you're looking at a black hole that is in a quiescent galaxy, one that does not have an active nucleus, that is not a quasar, the best thing to do is to look at the motions of stars or gas in the immediate vicinity of the black hole, and that can tell you what the black hole mass is. If you have a quasar, an active galaxy, and these are the things that I work on, then you've got a black hole that matter is flying onto it and gets heated up to very high temperatures and very luminous, and you can see these things all the way across the universe. So they're really great for cosmology because you can see them at very large distances because they're so bright. But what we do to measure the masses, we use a technique that's called reverberation mapping. The central accretion disk varies in brightness with time, and and the gas clouds swirling around the black hole in immediate vicinity respond to that. And if you know how fast those clouds are moving and you know the distance from the light travel time, then you were able to infer what the mass is. So that's what that used to be my day job. So.
There was one question here that came up, and this is sort of one of our tropes here on the channel, is, hi Emmanuel, Maxim asks, will LUVOIR and Webb use reaction wheels for tracking like Hubble, or some kind of different method?
Oh gosh, you know, off the top of my head, I can't recall, but I'm sure that we'll be using reaction wheels for steering, because, you know, we want to be able to slew across the sky faster than JWST does.
So just as a person who's reported on these things for a long time and watched the downfall of many spacecraft, allow me to offer you one recommendation: more reaction wheels.
Yeah. You know, reaction wheels and gyros and batteries are the super non-sexy things that nobody really wants to work on, but they're essential. They are the things that make a mission go.
Yeah, I mean, Kepler is dead because of reaction wheels. Hubble had to be repaired because of reaction wheels. So many spacecraft out there. So I think really you can never have enough reaction wheels. Is I guess what I'm really trying to drive at here.
They are getting better. The ones that were put on Hubble in 2009, in 9 years we've lost one, I think, and there's one that's a little flaky, but you know, they can operate with 3, and they've still got 5 that are working. So it's
yeah. There's a couple of questions here as well. Raj, a couple of people have been asking about the BFR, the SpaceX BFR, and actually you mentioned that earlier, which is you're waiting on the specs for the BFR. If the BFR shows up.
Well, right. Well, we need to know, you know, mass to orbit, and we need to know fairing size. And I think that, you know, from what we've heard so far, the big limitation is going to be fairing size. So again, you can get around fairing size. In fact, when we talk about really large telescopes, we talk about the tyranny of the fairing. You're totally limited by how big a mirror that you can put in a rocket fairing. So that's the sort of thing we say, well, maybe we got to send these things up in very large pieces and put them together.
Now, you sent me a copy of sort of a presentation that you're working on, and you've got a really cool image of what the telescope could look like. So I'm going to just take a second here and show people this, because I think it's really interesting. Let me see if I can bring this up now here. So on the screen right now, you can't see it, but people can see it, is the stowed 9-meter on-axis old, which shows what it could look like in sort of a top-down view and a side view of it.
Yeah, that's a 5-meter fairing.
And what's a rocket that holds a 5-meter fairing?
That's the oh gosh, I think New Glenn and Falcon Heavy. I think those are. I think the Atlas V has a 5-meter fairing. So yeah, I mean, these are fairings that at least notionally exist or will exist. Yeah.
And then the next slide here is it deployed, showing a person standing beside the fully unfurled telescope. And I guess the lesson that it's going to have to learn is how James Webb was able to unfurl, and if that technology was the origami of space telescopes.
Yeah, this LUVOIR has a lot of heritage from JWST. We learned a lot of lessons. We learned, in many cases, how to do things right, and we've also learned how to do things not right. So, yeah, we're very conscious of this, and we have a couple members of our STDT who have been working on James Webb for a long time, and in particular, one of the engineers who he says the reason he's on the team is to make sure that we don't repeat mistakes.
Right. Oh, that's good. That's good, because they're all getting a little bit of attention right now.
Yeah, that's right.
Now, you had one other idea as well, which is sort of like an alternate version of the smaller version of the telescope, and that's one that's off-axis to fit in a smaller fairing?
Yes, that's right. It requires a smaller fairing, basically because you need that off-axis structure that goes along with it. But the idea is that the diffraction pattern from an unobscured primary mirror is much simpler, and then therefore the coronagraph can be simpler. I mean, everybody's seen pictures from Hubble, for example, and you always see these diffraction spikes off the bright stars. And that's all due to the spider that's holding the secondary in place. So if you can remove that whole structure, then you don't get the linear features that cross the stars, cross the bright stars.
Yeah, you can get that with, you know, if you've got a Newtonian telescope and you've got that secondary mirror, and you'll get the diffraction spikes as well.
Absolutely, that's right. That's
Yeah.
right. So anytime you have an obscured primary, your diffraction pattern is going to be complicated, and therefore the coronagraph, which is designed to block that diffraction pattern, the light diffraction pattern, it has to be more complicated.
Now, it is interesting to me, just to go back to the rockets and the fairing sizes and things like that. I mean, what would be your perfect fairing to develop the kind of telescope that you would want to launch, obviously within the laws of aerodynamics? What would that look like? I mean, it's funny to me that you're having to sort of fit what is going to be hopefully the flagship telescope for the far, far future. You're still having to fit it within various kinds of capabilities. But if you could write a memo to SpaceX or to the people working on the SLS, what would it look like?
Well, let me put this another way. The question that I would like to know the answer to is, at what point does it become cheaper and or less risky to assemble a big telescope in space as opposed to deploying it autonomously? So what we're looking at for LUVOIR is a 15-meter telescope that deploys itself the same way that JWST does. But what if we could get all the components up there in 3 launches of smaller vehicles, and all we have to do is assemble it in space? Now, you know, at some point that becomes not a crazy idea. It becomes not crazy if you have the infrastructure to do it. If, for example, you have a deep space gateway, and that somebody else has paid for, because this is the whole thing. There's no way that the Science Mission Directorate can afford to do servicing missions on its own. It has to be an agency priority, and that essentially means you're going to have to involve human exploration and operations, and you know, use some combination of astronauts and robots to assemble and service telescopes. So you have robots do the things that good robots are at, and you have astronauts do the things that astronauts are good at.
And so then what would that look like? What would the capabilities be if you went down that pathway?
That's when you can really start to dream, right? you can imagine that if you're assembling something in space, you know, the limiting factor is going to be, okay, how many launches?
All right, let me try stopping my stream. I wonder if my... Yeah, it's frozen. Oh, it's back. Okay. That was close. Cool. I didn't have to restart my router and restart my YouTube and restart my everything. That's good. It just like disconnected my connection to YouTube at some point. So I have a 300 megabits connection, and that's still not enough. All right. So then, I mean, if you do have multiple launch vehicles and maybe even smaller launch vehicles, I mean, then you look at something like, say, you do have some astronauts in space. They're capable of configuring things in space, and maybe you just buy small Falcon 9 launches for $60 million a launch, and have the parts all just arrive at the L2 Lagrange point in waiting, and then some astronauts spend a couple of months bolting the whole thing together and aligning the instruments. Would astronauts aligning the instruments be high enough precision?
Well, you start by putting things together using kinematic latches, and that gets you down to about micron sort of accuracy. And then beyond that, then you're going to have to use various kinds of drive mechanisms that they use to align segmented mirrors on the ground as well. That's where you do the high precision stuff. So again, these things are difficult, but not impossible.
Because they spent, I know, like with the Giant Magellan Telescope and things like that, they've been spending, in some cases, years polishing these mirrors to try to get them perfectly,
Yeah.
you know, optically perfect. You would have to do the same thing and then take those up to space and then try to align them and make sure that they're perfectly aligned. But I guess you would.
And 30 years ago, I would have had real serious doubts about our ability to do that. But you know, what happened with you know, the Keck telescopes came together so quickly and were operating so quickly, I just couldn't believe it. And you know, we've used some of that technology with LUVOIR. And you know, if we're going to start assembling telescopes, we're going to have you know, more active support of the mirror segments in order to align them properly. But again, that's done routinely on the ground.
And doesn't that feel like a really worthy mission of a human space program?
Yes,
you know,
absolutely.
have you talked to astronauts at all about, hey, do you want to assemble the telescope in space?
Oh yeah, yeah. I must know, I don't know, a dozen or so astronauts, and basically they all seem to be in agreement that servicing telescopes in space is one of the things that's really worth their while and that they're willing to put their life on the line for.
Right. Which is, of course, a question that astronauts always have to ask, right? Is, am I willing to die for this telescope?
Yes, exactly.
Right?
Exactly.
Yeah.
And as astronomers, we're humbled by this. I mean,
Yeah.
it's amazing that they think that what we're going to do with these telescopes is so important that they're willing to risk their life to do it.
And every astronaut that you've talked to has said, sign me up, I'm ready to go.
Yeah, that's right. Yeah, well, that's an astronaut mentality.
That's kind of how they're wired. Yeah.
Exactly.
Yeah.
But you know, these kinds of missions. You know, I like the phrase that the associate administrator for the Science Mission Directorate, Thomas Zurbuchen, he refers to missions like LUVOIR as civilization level missions because they change how human beings think about themselves.
Yeah. And when you think of some of the budgets that are out there to buy things, money spent on various operations, the F-22 Raptor, the amount people spend on cigarettes, lawn gnomes, you know, chrome plating their trucks, that wouldn't it be amazing to send up a spacecraft that is capable of answering this most fundamental question that human beings can ask themselves, is, are we alone in the universe?
And yeah, I think it's a really important question for us to address because that will change no matter what the answer is, it will change how we think about ourselves. And we can do this, you know, for ballpark, the same cost as an aircraft carrier.
An aircraft carrier, there you go, done.
Yeah.
You know, one less aircraft carrier, one more fundamental answer to the most meaningful question that a human being can ask.
Right. And I'm not disparaging aircraft carriers.
No, they're fine. They're cool boats.
Yes.
But boy, wouldn't it be nice to have that answer?
Yes, exactly.
Well, we're just getting to the point now where we need to start wrapping things up. But so where can people how will people watch this unfold? So if they're excited about the future for beyond James Webb, beyond WFIRST, we talked about those other 3 telescopes that you're not involved in, but there's LUVOIR. What's the timeline from here on out, assuming everything goes perfect?
If everything goes perfectly, right? The decadal survey comes out and says we want LUVOIR, and you know, in fact, I think we made this progress if they say LUVOIR would be our top priority if we knew we could afford it, but you know, it's going to be really expensive. Even that gives us room to go. And in fact, at that point, that's when the public can become really important to us because they can say, you know, we really need to provide the Science Mission Directorate with, you know, a few extra billions so that they can actually build this civilization level telescope, something that's going to last for 50 years and is going to answer really fundamental questions. And you know, right now, the entire NASA budget is 0.5% of the federal budget. It's very, very small. The highest it ever was I think, was it 2 to 5% back in the Apollo era. We don't need that kind of. We just need a small augmentation. Really, the NASA budget hovers around 20 billion a year roughly, and we're looking at saying, well, if you can increase that temporarily by 10 to 20%, we're there. We can do this.
Yeah. So Decadal Survey forms, provides its recommendations by 2021.
Right.
Development of the spacecraft, it gets selected. When do we see it blasting off to space?
The most optimistic number, the one that we're using for costing purposes and planning purposes, we're looking at 2035.
Wow.
Yeah, it's a big deal. I mean, these things don't happen overnight.
Yeah.
Yeah, I mean, Hubble and Webb have had similar development times, we're doing things that are hard. We're doing things that nobody's done before. So we can't always cost them accurately because it's new. It's completely new, and we run into problems that we never expected. So This is why NASA missions are required to go in with a pretty generous contingency on their budget. But nevertheless, sometimes you run into bigger surprises than you anticipate.
And so then, and if people want to watch this unfold, what is the sort of best way to stay on top of what's happening with LUVOIR and the rest of the Decadal Survey?
There are websites that are going to be dedicated to the survey. There are also, each of the missions has its own website, and we try to keep these up to date as to where things are. The institutions that are going to host these telescope studies have websites for them, and you can always go to the NASA Astrophysics website at headquarters, and they have links to all of these missions, and they keep pretty much up to date on what the status is. So the next milestone that we reach, within the next few days, we will release our interim report, which we submitted a couple of months ago. Has been reviewed, suggestions were made, and now we're revising it, and now NASA's going to make it public. And that'll form basically the core of our final report, which is due in a little less than a year.
Right.
And then that will then go to the Decadal Committee for their consideration.
Now, I had one question I just wanted to stick in there because Zior asked it a bunch of times, and I will get back to it. But the gist was, although it's a different instrument, James Webb is going to be looking right back to the point that galaxies are coming to those first initial galaxies. What is, if LUVOIR does come online, what era is it going to be looking at?
It will look at the same era, but it will be looking at shorter wavelengths due to the high redshifts of the objects that we're looking at. So you'll be looking at rest frame far ultraviolet.
But isn't there sort of like these earlier ages, like the era of the first stars forming, the era of recombination and things like that, right?
Well, LUVOIR will be much better at looking at the hot gas that's involved in the assembly of galaxies, as opposed to stars in the dust, which is primarily what you're going to get with JWST.
Yeah, it's amazing how much farther there is still to look. When you know what the capabilities of Hubble are, even the capabilities of James Webb, there's more universe out there that still needs to be observed.
That's right.
Well, Brad, thank you so much for taking the time to talk with us and with the people watching the show today. Once I brought up the whole concept of LUVOIR, people have gotten more and more excited about it. I think we're going to definitely take another look at it again as the Decadal Survey comes together, but it was great to have you here and join us directly and be able to talk about the mission. And please, once you have a more final recommendation for NASA, please come back and we can take another crack and answer some more questions.
Great, I'd be delighted. Thanks
Wonderful.
very much.
All right, thanks everyone for watching, and we'll see you all next week.